All right, so electromagnetic wave. Here's Steve. All right, so here's what electromagnetic waves look like. They have they're oscillating electric and magnetic fields that are perpendicular to each other. Um, and they travel through space. So the cool thing, you remember with electromagnetism how we said fun fact number 3 was if a conductor experiences a changing magnetic field, then current is induced. Turns out if you dig a little deeper in physics, a changing magnetic field creates a changing electric field. And if you dig a little deeper, a changing electric field actually creates a changing magnetic field. But I thought a changing magnetic field creates a changing electric field. It does. But doesn't that create a changing like magnetic field? Yep. And doesn't that? Yes. They self-perpetuate each other. So the changing electric field creates a changing magnetic field, and the changing magnetic field creates a changing electric field, and like they just go through space, oscillating at right angles to each other. That is why they don't need a material, a medium. They can go through space, and it's a good thing. That's how we get sunlight. Okay, so if you to write something down. Electromagnetic waves are oscillating electric and magnetic fields at that are perpendicular to each other. Yes, it can travel through space because changing electric and magnetic fields, unless you create changing magnetic and electric. I don't know if that's going to make sense to you, but they create each other, travel through space. Yeah. Good. So they look like that. The speed at which they travel through a vacuum or travel through space is 3 times 10 to the 8th meters a second, which is the speed of light. And we give it 3 times 10 to the 8th meters per second. Okay. The speed of a wave is equal to speed is equal to frequency times wavelength. The special case scenario for this guy is they all travel at the same speed, is the speed of light. You actually did that equation in chemistry. Okay, so that's just a special application of this equation. Okay, so they all travel the same speed. Good? Okay, so this is a chart of the electromagnetic spectrum. We're going to take a tour of that today. So, there are 7 categories, and we're going to rank them in order of longest wavelength to shortest wavelength. It goes from 100-meter wavelength to times 10 to the negative 12th. So it's a huge spectrum. Okay? So we know that they all move the same speed of light. So as the wavelength decreases, what happens to frequency? Everybody see that it goes up? Okay. So as you progress this way, the wavelength gets shorter, and as you progress to the left, it gets longer. Frequency, you get a higher frequency. And you get lower frequency going to the left. Okay. So we're going to take a look at each of these 7 categories and how they are applied in life. Good? Okay. First, radio waves. These have the longest wavelength. Obviously, radios, so AM, FM, XM, all of those, like your radio stations, those have those are the frequency at which they are broadcasting their specific radio waves, and they had information on those. TVs, satellites, anything we use to speak to satellites, these are all radio waves. Okay. Next up are microwaves. So microwaves, cell phones use microwaves, Wi-Fi, Bluetooth, radar. These are all examples of microwaves. So microwave ovens, that's probably if you're like, hey, where do you find microwaves? Well, in the kitchen. So microwaves are somewhere in this realm here. Okay, there's a whole smattering of different frequencies, one of which is the natural frequency of which water molecule vibrates at. That is the frequency that microwave ovens produce. That's how they heat your food. I don't know if you've ever paid attention to like what foods warm up better in a microwave, but dry foods don't do really well. You need to mix it with some water, and it'll do better, a lot better. Okay, because what it does is it has that frequency, and it causes the water molecules in the food to like vibrate, and that's what warms them up. You good with that? Okay. So a popular thought is like, oh my goodness, wait a minute, cell phones use microwaves? Like you're like zapping your brain with microwaves. Like that would be bad. It would be bad. Okay. That's like, has your mom ever yelled at you like, quit sticking your head so close to the microwave door? Yes, no. Okay. This mesh screen actually to a microwave looks like a mirror. Okay. But some of those do get out occasionally, so it's good advice like, come on, hurry up. Like that's not good. Like there are probably some rogue microwaves. Like your brain's full of water. Like most of the water is not good. So like give it some distance. Okay. But we stay way away, like I'm making this up, microwaves, like the frequency that oscillates water, resonates water, is like right there. Everything else we kind of stay away from. So when like cell phones, we're way away from that frequency. Okay, you're good. You remember the tuning fork demonstration where like I hit it and it resonated the other one? And I changed the frequency of one of them and didn't touch it. It's the same idea. Okay, we're fine. So Wi-Fi and Bluetooth, this is like, by the time you guys, kids are taking physics, we probably will subdivide this because we're packing this out with different applications. The longer the wavelength, the further these can travel. And so the biggest distinction between Bluetooth and Wi-Fi is Bluetooth has a higher frequency and doesn't go as far. Wi-Fi has a little lower frequency and travel further. Okay, if we could see into the microwave spectrum, this room would be full of them. Like if your cell phone Bluetooth function is on, it's emitting Bluetooth. It's emitting microwaves. Like the routers are all, anything wireless, it's emitting electromagnetic waves. Okay, so this is how we pass information around wirelessly. A lot of people are asking, like, hey, how does stuff work? Like, how does it go from my phone to my AirPod or whatever? So when we were doing electromagnetism, talking to a microphone, it takes those sound waves and it changes them to vibrations of alternating current. And we take that alternating current, we pass it to a speaker, and that causes that. Okay, all we need to do to pass information is pass vibrations. And so these electromagnetic waves, we can alter the frequency and the amplitude and put information on these electromagnetic waves that we can broadcast from an antenna, and then you have a receiver. So your cell phone would be broadcasting, your AirPods would be the receiver, and it's going through the air. Cool with that? That's what's happening to all wireless stuff. It's through electromagnetic waves. Cool with that? Next up is infrared waves. This is how remote controls work, IR. So if you look at my remote here, okay, there's that light bulb is emitting infrared waves. You can't see it, but your camera on your cell phone can. So get rid of that. Okay. And those of you in the video, you wouldn't be able to see that if you're just looking at it with your eyes, but the camera can. Okay. So infrared also corresponds to anything that is above absolute zero emits infrared waves. You emit infrared waves. As things get hotter, they emit high enough frequency to actually go into the visible light category. So if you like stick your hot dog roaster in the fire for too long and pull it out, it's glowing like orange. As it cools down, it's going to go to red and then black, but it's still emitting infrared waves. Okay. So, in fact, everything that is above absolute zero emits infrared waves. So we have cameras that are sensitive to design for picking up infrared rays, and these are known as thermal imaging cameras. Okay, and these are really cool. You can like see different things. So this is how Predator sees thermal imaging. You can look at your house to see where you're losing heat. Another application is like trying to figure out where a clogged pipe is, and have hot water go down the pipe, and you can see where it like changes temperature, and like aha, the clog's right there. So there's different ways you can apply that, but it's a whole nother realm of information with heat. Cool with that. And then we get to visible light. Okay, so this is part of the electromagnetic spectrum that we can see: red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Notice how small of a section that is in the entire electromagnetic spectrum. Just a small fraction. And that our eyes are sensitive to. Cool. After that, we get ultraviolet. So you have like infrared, ultraviolet corresponds to red, violet. This has to do, like, insects can see into the ultraviolet ray. Sunburns that correspond to that. Okay. So, check this out. So, energy associated with electromagnetic waves is proportional to the frequency. So, as the frequency increases, so does the energy. Cool with that? Okay. So, you see this wavy stuff in the background here? Okay. This is how much of, like, what frequencies get blocked by our atmosphere. So, all of the, like, here we get sunlight, like, light gets through, which is a really good thing. We can see the stars, we can see light from the sun, like, this is a really good thing. We try to use, like, send and receive information in radio waves, like trying to see if there's life on other planets with the radios. Okay. From here on out, this gives us cancer. From here on out, this gets blocked by our atmosphere. Whew, that's a good thing. Okay, let's take care of our atmosphere. Okay. After that, X-rays. Okay, so X-rays have a short enough wavelength that they can go through soft tissue, but they can't go through dense tissue like bones and stuff. This is actually a photograph of an X-ray to look to see if broken bones are broken. We do the negative of that, the inverse of that. If you ever taken photography, X-rays gives you cancer. You don't want to be exposed to those too much. So that's why when in the dentist or the doctor's office you're wearing a lead smock, it's dense enough that it blocks it so it doesn't get through. If you ever do become an X-ray technician, make sure you protect yourself behind walls. Like, don't just be sitting in the room with the patient as like the camera's going off, emitting X-rays. Okay. And the last one is Gamma rays. This is what we associate with like like radiation. Like, oh man, this is bad. It is, but technically, all types of electromagnetic waves are radiating. Like it's all considered radiation, but we just associate when we say radiation, it's like bad radiation with gamma rays. Good at that. Okay. So if you could see into the electromagnetic spectrum at the sun, you'd see this for radio waves. This would look microwave, infrared, visible light. I don't know why they didn't make that yellow. I mean, obviously it is. Ultraviolet, X-rays, that's pretty crazy. And gamma rays, that's what the sun looks like in terms of emitting gamma rays. So the sun emits all those types of frequencies. We need our atmosphere to block out the higher end. Okay. Everybody good with all travel the same? Highest frequency, D, gamma rays. Longest wavelength, radio. Most energy, gamma. Okay. So you know your 7 categories, how they rank. Okay. We've actually used Doppler effect to determine that the universe is expanding. So, did you guys ever do this in chemistry? These things? Regular chem? Thumbs up if you've done these. Like the light, fluorescent light. Here's the review worksheet, printed them off. They're also on Canvas.
And it's over ecology, so it's supposed to be really hard. It makes everything hard. How is that wow. Like all you have to do is that. That's surprising. Yeah. I'm questioning the way they're worded. Okay, that was it. When today we did the and then there's also like math. So I don't know
You're sweet, you're so sweet.
Yep.
here's mine.
Isaac.
But why were you giving why did you show up?
Oh, yes, I see
You
that.
just look like
Hey.
Yeah, I had a dentist. It's like, too late.
All right, you guys do this in chemistry? Okay. So different. See ya. Thanks, Ashley.
We have a test.